Alright, in this example, we're asked to find the internal shear and bending moment as a function of x for the simple beam shown. It has a 20-foot span, and the concentrated load is 30 kips, and it's applied 15 feet from the left support. So let's get all this laid out here. It may not be drawn perfectly to scale, but what we've got here is something that looks like that, and it says as a function of x. Well, typically we'd probably put our coordinate system over here at the far left, so we'd call that then as a function of x. Right? And anytime you see a concentrated force here, you got to start thinking about multiple free body diagrams about what happens on either side of the concentrated force, because remember, the definition of a concentrated force is this total force magnitude, but we assume that it's not spread out over any length, right? It's as though it could happen at an infinitesimally small location. Right, so let's look at a free body diagram where x is less than 15 feet. Right, so in other words, anywhere over here to the left. And when we do that, there's our beam segment. It goes over at an x distance, and unknown, it's variable, and there's no applied loads in that segment externally. We do have a reaction that, let's see here, there's A, let's call that B, and so there's an AY, there's a BY, and I hope at this point you've kind of begun to figure out that, hey, if I sum moments about point A, the 30 kip will have a 15-foot moment arm, BY will have a 20, and 15 over 20 is 3/4, so BY is going to be 3/4 of the 30 kip, and AY likewise would be 30 times 5 divided by AY times 20, that would be a 5 over 20 moment arm, so it would take 1/4 of the load. Right? So that vast majority of the load goes to the closest support in its effect. Right? So our reaction there is 7.5 kips. Alright, now we have a right hand exposed face, so the positive shear is acting downwards. Of course, the positive axial force would be in tension going to the right, and it's going to be trivial, it'll be 0, right? And then we have the positive bending moment then is shown in a smiley face kind of fashion there, right? So that would be counterclockwise on this right hand exposed face. And now we just go execute our equilibrium that we've got. That okay? Sum of forces in the x, take to the right positive, equal n, equals 0. Sum of forces in the y, let's take upwards positive, we get 7.5 minus v, and that's equal to 0. And so v equals a positive 7.5 kips no matter where we're at in that segment. It's not a function of x. Right? Let's now sum moments. I like to sum moments about the point in question. I'm going to call that point 0 for the heck of it. Take counterclockwise positive. So I'll have minus 7.5 kips times x. Oh, there's your moment arm in there. The v goes through that point. The n goes through that point. And then so plus m, and that's equal to 0, and therefore our m is going to be equal to a positive 7.5 kips times x. And x will be in feet, so I'll have kip feet for the total units of the moment, which makes sense. And it means that the moment is increasing linearly with distance away from the support. Okay, that's interesting to know. Right? So let's go do a free body diagram, not at x equal to 15, but rather, from 15 to 20 feet. And I could do two different free body diagrams here. I could do one that goes from the far left all the way across the point load, and now the force shows up. There's your 30 foot or 30 kips, and there's your reaction, 7.5 kips, and my distance x would be all the way over to here, and the distance from the load over to that point would be x minus 15, because x is greater than 15, right? And then I would show the internal shear, the internal axial force, which we know is 0, and the internal bending moment. That would be one way to do this, right? That looks kind of complicated. I don't like it. I don't have to use that one. Why not use the right half? Okay, and yeah, why not? And so let's see what that would look like. We've got a reaction of By of 22.5 kips going up. We have the shear acting upwards positive, and we have the bending moment. Now clockwise, smiley face, right, because we're on that left-hand exposed face. And of course the axial force is 0. I don't really want to show it. Complicates things. That's a lot simpler looking free body diagram, isn't it? And the distance that we have here to the point of interest is going to be 20 minus x, right? X is between 15 and 20. When x is equal to 20, then 20 minus 20 is 0. We're all the way out to the edge. When x is equal to 15, then that would be a 5-foot distance, right? So that all works just fine. I think that looks easier to work with. That's the one I'm going to write our equilibrium equations to find the shear and the moment as a function of x, right? So we'll sum forces in the y. I'll take upwards positive. That will be positive v this time, plus 22.5 kips has to be equal to 0. So now the shear is a negative 22.5 kips. And it's not a function of x, it's just a function in that region anyways. It's a constant value no matter where we're at in that little small region. Right? And then we'll do summation of moments. And let's take clockwise positive this time. So we'll have m minus, now the v doesn't get in there, so minus 22.5 times 20 minus x. And that will be equal to 0. So that, of course, when we take that to the other side, m is equal to a plus 22.5 times 20, or 450 kip foot. And then minus times a minus is a plus, but take it to the other side, it becomes a minus again. Minus 22.5 kips times x. Ooh, that's our function. Wow. Well, hey, when x is equal to 20, then, oh, wow, how about that? M at x equal to 20 is going to be equal to 0. When m is at x equal to 15, our moment is going to be equal to 112.5, which, so by the way, is the same thing as 22.5 times 5 feet. That's the same answer either way. That's kind of interesting, huh? Equilibrium applies here. And wow, hey, I got an idea. Let's cut the beam infinitesimally close to the load on either side and see what happens here in that free body diagram. So free body diagram at x equal to 15. Now that's in quotes because we can't really split a load. That's not possible to split a concentrated force. We have to go to one side or the other. In this case, we're going to do both sides. It's going to be infinitesimally close. There's your 30 kips. And notice something here. The shear to the left of that point versus the shear just to the right of that point are shown like so. And then here's our bending moment to the left of that point, bending moment to the right of that point. Right? Now this little delta x that I've shown is going to 0. Right? We're just immediately on either side of that. But we are definitely on either side. And when we sum forces in the y, let's take upwards positive. We'll have v to the left minus 30 minus v plus to the right equals 0. Then 30 comes over to the other side. No, I don't want to do it that way. I want to have v plus minus v minus, and that will equal minus 30. Why did I want to do it that way? Because plus meant to the right, and so as we're marching left to right, the delta v is going to equal this concentrated force. It's going to go down by 30. And is that not what happened? We started at 7.5, and then immediately that load dropped us by 30, and we went to a negative 22.5. That's pretty interesting. Then look at the moments, right? Everything, remember, delta x goes to 0, so when we sum moments, all of those forces, the v minus, the v plus, and the 30 go right through that point, and we're just going to have, in the sum of moments, about this point, we're going to have that those two moments are going to be equal to each other on each side of the concentrated force. And that's what we're going to find out, right? We got a positive 112.5 here. We didn't do the math yet, but m at 15 using the one we had before was 7.5 times 15 equals 112.5 kip foot, which was the same. Oh, that was the reaction times that distance of x equal to 15 foot. Wow, those really do work out to be the same on either side of this concentrated force, whereas the shear had a delta difference that was caused by the concentrated force. Now we're going to do a lot more with this in the next couple of lessons as we work through this. This would be called the equilibrium approach to finding the internal shear and moment as a function of x. Right? Oh, hey, by the way, why the heck do we care about these functions? Because we have to design the beam. And we have to figure out what the largest internal demands are, the largest internal shear and the largest internal bending moment, in order to be able to size the beam. That's why we care.